Okay, here we are again with, I think this will be our final video on section 3.3. So let's get started. Again, section 3.3. And we're going to continue our discussion of concavity and inflection points. Just as a reminder, recall, we discussed last time that if a function is concave down over an interval, then the second derivative, f prime prime of x, is negative in that interval. And if a function is concave up in a certain interval, then the second derivative, f prime prime of x, is positive in that interval. That was kind of what we talked about last time. We can actually use this to test for local max and min as well. We have one test, the first derivative test, that we've used to figure out if a critical point is a local max or a local min. We can use the second derivative as well in a different way to test if a critical point, at least a specific type of critical point, is a relative max or min. So let's talk about that. There's a test called the second derivative test for local extrema. And it goes like this. If the second derivative, f prime prime, we have to first of all state that it is continuous. So that derivative exists for all x, or at least it exists at c. So I need to check, does it exist? It exists at x equals c. And we have the criteria that the first derivative at that point c is equal to 0. So this is one type of critical point that can be found. This is the type that occurs when I have a local max or min for the tangent like that. This will not work if I have a critical point for which that first derivative does not exist, only for this criteria. But if I've got that, then I can say, well, three things. If f prime prime of c. So note that, again, this tells me that c is a critical number. C is a critical number. And then if I evaluate the second derivative at c and I get a positive number, then this point c, f of c, is a local minimum. Similarly, if the second derivative evaluated at that critical point c is negative, less than 0, then this point c, f of c, is a local maximum. If we happen to get the case where the derivative evaluated at the critical point is equal to 0, then I am out of luck. The test did not tell me anything. And you might ask, well, why does this test work? Let's figure it out. If I have something like this, where, okay, I have this critical point, C. Okay. And that C, I can tell from this graph, is a local minimum because it is a low point on the graph. Here, C is, well, CF of C. I should probably write that in there. Here, CF of C is a local minimum. And this is the case where that second derivative, f prime prime, at that point C, well, the graph is concave up here. So that means that that second derivative is positive. And I have a critical point right here at the very bottom of this concave up portion of the graph. So if I have these two features, that the second derivative is equal to 0, and at that particular critical point, the first derivative is equal to 0. Excuse me, the second derivative is greater than 0, and at that point, the first derivative is equal to 0, then that classifies CF of C as a local minimum. I could say something very similar for the other case. Let me use black. This is my graph. This is my point C. And C happens to be a local maximum. Okay, it's here. So this is the point C, F of C. I can see that CF of C is a local maximum. All right, and I can also tell that this point CF of C occurs at the very top of this concave down portion of the graph. So because of that, F prime prime of C, the graph is concave down there, so it is less than 0. So if both of those things occur, then I have a local maximum. Why might we want to use this test? If I have a perfectly good first derivative test that I know pretty well, and sometimes this test can fail me. Well, one reason would be, let's see, you might note the second derivative test only requires us to put the critical points into a function once rather than two test values for each critical point. So there are less calculations required for the first derivative test. Second derivative test, excuse me. For the second derivative test. Also, if I use the second derivative test, then that tells me a little more than just this is a maximum, this is a minimum. It tells me what type of maximum or minimum. In other words, the shape of the graph around the critical point. Also, the second derivative test, it tells something about the shape of the graph around the critical point. Around the critical point. So there's two benefits, and we should know how to do both the first derivative test and the second derivative test. So let's do an example of how we would use this. Let's let f of x equal 2x cubed minus 3x squared plus 12. And let's do this. Let's find all relative extrema. Using the second derivative test. The second derivative test, and I will say if possible, because it's not always possible. The second derivative test where possible. Okay, so let's do that. I need to first of all find the critical points, which means I need the first derivative. F prime of x is equal to 2 times the derivative of x cubed, which is 3x squared, minus 3 times the derivative of x squared, which is 2x, plus the derivative of 12, which is 0, which gives me 6x squared minus 6x. All right, well, while I'm in the differentiating mood, how about I go ahead and find the second derivative as well? F prime prime of x is equal to 6 times the derivative of x squared, which is 2x, minus 6, which gives me 12x minus 6. Okay, so I have both of those derivatives. Let's find the critical points, because those are the only places where the local extrema can occur. Find the critical points. This is where, well, one way to find them, or one location, is where the derivative is equal to 0. So I'm going to set that derivative, 6x squared minus 6x equal to 0, and I'm going to solve. I can factor out 6x, and I get x minus 1 is equal to 0. Go ahead and go to the next page. So I get 6x times x minus 1 is equal to 0. Two factors, I'm going to set them both equal to 0 and solve. 6x is equal to 0, or x minus 1 is equal to 0. Left-hand side, I'll divide both sides by 6. And you get that x is equal to 0. Right-hand side, I'm going to add 1 to both sides, and I get that x is equal to 1. So I have two critical points, two possible locations of relative max and min. I should go ahead and note, I'll put the derivatives over here. F prime of x is equal to 6x squared minus 6x. F prime prime of x is equal to 12. Places where the first derivative does not exist. Well, that first derivative is a polynomial. It exists everywhere, so I don't get any critical points from that categorization. Okay. So there's that. Let's see here. Now that I have the critical points, I'm going to use the second derivative test to classify them. And actually, I'm going to draw a little number line just like I did previously. Okay? These are my critical points, 0 and 1. And I'm going to test those critical points in the second derivative. I'm not going to choose test values. I'm actually going to put the critical points themselves inside the second derivative. So as a reminder, second derivative, f prime prime of x is equal to 12x minus 6. So let's see here. F prime prime of 0 is equal to 12 times 0 minus 6, which is a negative 6. All that I really care about is the sign. The sign is negative here, therefore the graph is concave down. Let's test the other critical point. F prime prime of 1 is equal to 12 times 1 minus 6, which is equal to positive 6. I care about the sign, which is positive, so the graph is positive in this interval. Therefore, the graph is concave up. This critical point lies right at the top of that concave up portion. This critical point lies right at the bottom of that concave down portion. So by the second derivative test, this critical point x equals 0 is a relative maximum. And by the second derivative test, the second critical point, 1, is a relative minimum. I can state that by using that test. Okay? Let's do one more. Let's let f of x equal x squared times the natural log of x. And of course, I want to only consider this on the interval from 0 to infinity, because past that, or prior to that, to the left of x equals 0, this function is not defined. So I need first derivative and second derivative to start. F prime of x is equal to, by the product rule, I have two functions. Here's one function. Here's a second function. They're multiplied together. So I'm going to use the product rule to write the derivative. The derivative d dx of x squared is 2x. And the derivative d dx of the natural log of x is 1 over x. So I will use the product rule to put those parts together. F prime of x is equal to the first function, x squared, times the derivative of the second, which is 1 over x, plus a second function, natural log of x, times the derivative of the first function, which is 2x. I can write that a little bit simpler. X squared times 1 over x is x, plus the natural log of x times 2x. That's f prime of x. While I'm at it, let's go ahead and find the second derivative, f prime of x. And just for the sake of time, I'm going to assume that you know how to find it, so I'm going to do it quickly. It's 1 plus, using the product rule, 1 over x times 2x plus natural log of x times 2, which is equal to 1 plus 2 is 3, plus natural log of x, and I'm going to put the 2 out front. So that is the second derivative. My first derivative here, second derivative here, f prime of x. Okay, let's find critical points. Critical points, this is where f prime of x, excuse me, f prime of x is equal to 0, or f prime of x does not exist. I'm taking the first derivative, which is the function x plus 2x times the natural log of x, and setting that equal to 0. Okay, I think that I'm going to factor this. It looks like I have two terms involving x, and they both have a common factor of x. So if I factor that out, then I'll be able to set each factor equal to 0. Factor out x times 1 plus 2 times the natural log of x is equal to 0. So this means that x is equal to 0, or 1 plus 2 times the natural log of x is equal to 0. Well, this can't occur. That's not in the interval over which this function is defined, from 0 to infinity. So I have to throw that out. But on the right-hand side, I can solve for it. I'll subtract 1 from both sides. 2 times the natural log of x is equal to -1. I will divide both sides by 2. I get that the natural log of x is equal to -1/2. And now I can rewrite this in exponential form. E to the -1/2 is equal to x. Now it looks like we've solved for x. That is our one and only critical point for this particular criteria. Places where the first derivative does not exist, places where the first derivative does not exist, and specifically on the interval from 0 to infinity. Remember that the first derivative is equal to x plus 2x times the natural log of x. Well, the only thing that would make that not exist is if I were putting 0 or a negative number in the natural log. This restriction does not allow me to use negative numbers or 0 in the natural log, so there are no such values that make this not exist. Not applicable. So I don't get any critical points from that. All right. I'm going to put that one and only critical point on the x-axis. Don't really technically need it here, but I'll go ahead and do it just for the sake of form. I want to test the sign of that in the second derivative. F prime prime of e to the negative 1/2 is equal to 3 plus 2 times the natural log of e to the negative 1/2. This is equal to 3 plus 2 times natural log of e to the 1/2. Remember, this means log base e of e to the negative 1/2. So the base of the logarithm and the base of whatever is inside match. So this is equal to negative 1/2, which is equal to 3 minus 1 or 2. And all I care about is that it's positive. So second derivative is positive there. That means the graph is concave down. That is enough for me to be able to say that this is a local, this is the location of a local maximum. The second derivative test guarantees that for me. Okay, I think we'll stop there.